here today and have the opportunity to talk to you about the future of computer science. So one of the things that is important is that you're entering the information age. And just to set the stage for my talk, I'd like to tell you just a brief story of my career. I graduated in an electrical engineering department in 1964. One of the reasons I was in an electrical engineering department is that there were no computer science departments at that time. And I was hired by an electrical engineering department at Princeton, but fortunate for me, the chairman asked me if I would teach a course in computer science. And at the time, I had no idea what would go in such a course because there were no textbooks. But what I didn't realize is that teaching that course made me one of the world's first computer scientists. And so whenever our country was looking for a senior computer scientist, I was on the short list. And one of the advantages of that is at one time, the president asked me if I would serve on our National Science Board overseeing our National Science Foundation. I was in my 40s. Imagine if I had been in high-energy particle physics. I would still be waiting today for the senior faculty ahead of me to retire so that I would have that kind of opportunity. Now, when I tell this to students, they say, you were fortunate because you graduated in 1964, and today is 2012. But the message that I want to leave you in my talk today is that there is a fundamental change taking place. And if you position yourself for the future, you will have a fantastic career. Computer science is undergoing a fundamental change. In the past 30 years, we were concerned with making computers useful. So we were interested in programming languages, compilers, operating systems, algorithms, databases. And the emphasis was on making the computers useful. But in the future, we're going to be concerned with what we're going to use those computers for. And the things that you are going to be involved in is tracking the flow of ideas in scientific literature, the evolution of communities and social networks, extracting information from unstructured data sources, and many other uses like that. And what I'd like to do is talk a little bit about the drivers of that change. Part of it is the merging of computing and communications. And it may be that the communications is more important than the computing aspect. And just the wealth of data in digital form, the fact that there are networked devices and sensors. And this is going to have fundamental implications for theoretical computer science. We're going to need to develop the theory that is going to support these new directions, and we're going to have to update our computer science education. And so just what I'm going to try and do in this talk is give you a brief view of what the future is going to be. Then I'll talk a little bit about the science base that's needed to support that future. And then I'm going to try to answer a question that I'm often asked, and that is, what does a science base look like? Okay, so one of the things that Rick mentioned in the talk that you just heard is the big data. And just to give you some sense as to what we mean by big data, we broadcast enough bits that it's equivalent to approximately 174 newspapers per person in the world. And when you stop to think of it, you know, have you read your 174 newspapers today? There is so much data that you can't even look at it. You're going to need computer programs to extract from that data the portions of it that are of interest to you. To give you another example of the size, if you look at Facebook, they claim that they upload 250 million photographs per day. Also, one of the things, computer science is going to be involved in every field of science. Physicists have recently announced that they found a new elementary particle. But one of the things that I like to point out is that computer science played a key role. One of the things is they looked at proton-proton collisions, and they looked at 1,000 trillion of them. That number is so large that no person, the physicists, didn't look at them. It was a computer program that looked at them and found out which of these collisions were of interest. And it's this kind of role that computer science is going to play in basically every discipline you can think of. And one of the points I'd like to make is that our current database tools are simply insufficient to capture, analyze, search, and visualize the size of data that we're encountering today. So what we need is we're going to have to develop some more theory, and this is what you can do during your careers. And this theory will be concerned with large graphs. When I went to school, the graphs could be drawn on a piece of paper. They had 10 or 15 vertices. The graphs that you're going to be concerned with are going to have billions of vertices. You're going to be concerned with things like spectral analysis, high-dimensional data, and dimension reduction. And one of the things on this list which is of particular interest to me is sparse vectors. And one of the things that I would like to point out to you when you start to look for a research area, if you're listening to various talks in different disciplines, and some idea comes up over and over again, it's probably fundamental. And so that's this last item on the list, sparse vectors. And the question is, what is a sparse vector? Maybe it's a 1,000-dimensional vector, but it's all zeros for just 6 or 7 coordinates. And you might say, well, why are sparse vectors of any interest? And the answer is because they come up in many different disciplines. They come up in tracking the flow of ideas in scientific literature, in biological applications, and signal processing. And what I'm just going to do is take one application, just to show you in the biological area. One of the things you might be doing is you might have an orchard where you have apple trees. And what you want to do is try to develop some new apple trees which have apples with some property which is better than your current trees. So what you have is you basically have a matrix. Each row in this matrix corresponds to a tree in your orchard. The columns correspond to positions on the genome. And this vector, this long vector here is an unknown. And the short vector way over at the end is some observable phenomena that you want to improve. Maybe it's how bright red the apple is or something like that. And you would like to know what are the positions on the genome that give this particular property. Well, the way to do that is to solve this linear system of equations and determine what this vector is. But you immediately say, well, that doesn't make any sense because you have many more columns than rows, and so there's a whole vector space of solutions. Which one do you want? But it turns out that if you ask for a sparse solution, the sparse solution is unique. And this suggests that we ought to understand why. One of the things you might like to explore is what is the mathematical properties that says that there's only going to be a unique sparse solution. You can see physically why this is true. If there were 2 sparse solutions, that would say there are 2 different sets of genes which give rise to this property. But evolution is thrifty, and it would not evolve 2 different ways of generating the same property. So this is one of the reasons why sparse vectors are important, but also because they come up in many other disciplines. I'm going to talk a little bit about some of the things that you are going to do, some of the databases that you're going to construct. In the not too distant future, we're going to digitize medical records. And if I had an illness here in China, I'd be able to go to the doctor, and the doctor would be able to upload my entire medical history and give me the best possible medical care. However, I don't want my insurance company looking at my entire medical record. I don't feel that's any of their business. The only thing that the insurance company needs to know is that they owe some doctor some money. They don't need to know why. It's irrelevant what medical treatment I got. The only thing that's relevant to the insurance company is that they cover this treatment and that they have a rigorous proof that they owe this money. Now, also, researchers would like to look at this database, and they would like to look at statistical properties of it, but we want to design this database in such a way that no individual information is released. And these are the kinds of systems that you're going to have to create. And there's some relevant research going on. It has to do with zero-knowledge proofs and differential privacy. And what I thought I would do, since you might not have seen a zero-knowledge proof, is I thought I would just show you one so you'd get an idea that this can indeed be done. A zero-knowledge proof is simply a proof of a statement that the statement is true without providing any other information. And for a simple example, I'm going to assume that you all know how to play the Sudoku. So let's say I wanted to prove to you that I know how to fill in this board. Basically, what you do is in each row, each column, and each 3x3 array, you put in the numbers 1 to 9. Okay? And I want to prove that I know how to do this without giving you any information whatsoever as to how to do it. So how do I go about this proof? Well, what I'm going to do is I'm going to write my solution on little pieces of cardboard. And I've illustrated here the pieces of cardboard for the top row. And I'm going to put them down on the board, but upside down so that you can't see them. Okay? And now what I'm going to do is let you ask certain questions. You can say, show me the first row. And what I will do is I'll pick up the pieces of cardboard, I'll shuffle them so you don't know which was in which cell, and show them to you. And you will look and you will see that I indeed have the numbers 1 to 9 for that row. But I didn't give you any information as to which number was in which position. Then I'll put the pieces of cardboard back down, and you may check a column, you may check a 3x3 square, and pretty soon you're going to believe that I have a solution. Now, I should point out that this is not a rigorous proof in the sense that I've proved absolutely to you that I have a solution, because what you may not observe is that I may have put the pieces of cardboard back down in a different order than I picked them up. So all you know is that with high probability I have a solution. And by asking enough questions, we can reduce the probability that I don't have a solution to 10 to the minus 9th or something like that. Now you may say, well, this is a trivial problem. Can you do this for a more complex problem? And there's a problem of coloring a graph with 3 colors in such a way that no 2 adjacent vertices are the same color. And this problem is a hard problem. There's no known efficient algorithm for coloring a large graph. Okay, so let me give you, suppose I'm in a business where I color graphs and I want to do business with you, but you're a little nervous about paying me to see the coloring before I show you the coloring because you're not convinced that I can do it. And I'm a little nervous about showing you the coloring before you pay me because I'm not sure that you're going to walk off. So what we want to do in order to do business is I want to give you a rigorous proof that I have a coloring without giving you any information whatsoever about what the coloring actually is. So what I'm going to do is for every vertex in the graph, I'm going to take a little envelope, and I'm going to put in that envelope a piece of cardboard of the color for that vertex. And I'm going to seal them up. And now what you can do is you can ask me a question, just like in the Sudoku case. You pick an edge, and I will give you the envelopes corresponding to the 2 vertices, You open them and make sure that the colors are different. Now, I've given you absolutely no information about the coloring, because if I had a coloring, I could always permute the colors so that those two vertices were the color of that are in the envelopes. But just looking at one edge doesn't convince you that I have a coloring. You want to see the envelopes for another edge. But if I allow you to see the envelopes for another edge, then you get some information. So what I'm going to do instead is I'm going to take all the envelopes and I'm going to throw them away, and I'm going to start over. I'm going to take a new set of envelopes, and I'm going to permute my coloring and put the colors in, and then let you pick another envelope, another pair of envelopes. Now, you get no information because the second coloring is a permutation of the first, and you don't know that permutation. And as long as the two vertices are different colors, you have a little bit more evidence that I have a coloring, but you have no information as to what the coloring is. Now, after you ask me enough questions, you get convinced that indeed I do have a coloring. But you might say, well, this is going to take a long time. Well, the way we do this, when you do something like this, you're not going to actually use envelopes. What we're going to do is we're going to agree on an encryption system, and I'm going to encrypt the colors of the vertices, and then you're going to ask for the encryption key for two vertices, and I will give you those two encryption keys. And since we're going to do this electronically by means of a computer, we can do millions of edges per second, okay? So that's how these zero-knowledge proofs work. Now, the digitization of medical records is not the only system where there's a privacy concern. Almost every database that you're going to construct, this is going to have this kind of situation. So let me quickly talk about another example having to do with cars and roads. Quite often, I drive to a city called Philadelphia, and what I do, the route guidance system in my automobile takes me along these red arrows and down to where I get on this interstate highway. But since I go there frequently, I noticed that many cars turned off a little earlier and took a different route. So I started to take this other route, and it was a little faster. And then I noticed there was still a shorter route. And the question is, why did my route guidance system not give me this shorter route? And the answer is the route guidance system always keeps me on main highways because they don't know the condition of these back roads. But imagine if your automobile recorded its GPS coordinates. And every time you went in for service, it downloaded the GPS coordinates. And by using all of this information, the route guidance system could see how local drivers, what roads they took, and they could do a much better routing. And imagine that if they just reduced the amount of gas we consume by 1%, this is tens of billions of dollars. So these things are important. But there's a problem here. I don't want to download my GPS coordinates because that would tell you who I am from where my car is parked at night. It would tell you where I work from where I park it during the day, and it would tell you everywhere I go. And I'm not sure I want to give that information to you. So again, you're going to have to create a system which preserves this information. Now, in the past, sociologists could study groups of people with a few thousand individuals, but today we can study social networks that where we see the interaction of millions of individuals. And I'm just going to show you some of the things that you can do. One of the important activities is how communities form and evolve. The early work in this area had to do with something called min-cut. They divided the graph in half into two equal-sized pieces where there's a minimum number of edges connecting the two pieces. And there was a number of assumptions people made, but they were thinking of small graphs. With the graphs that you're going to deal with, you don't want to take a graph with 100 million vertices and divide it into two pieces of 50 million. What you want to do is you want to pull out a community with only 50 vertices. And so how do we go about doing that? And one of the things, the early work on communities sort of assumed that if there was a community, the people in that community had more links to people in the community than to people outside. But that's not true. This is a community. The blue area is theoretical computer science, and I put myself in there. But notice that I have many links outside that community. And because there are hundreds of millions of people outside that community, even though the probability I'll have a link to someone outside is lower than the probability of a link inside, just because of the numbers of people outside, I'm going to have many more links outside than I do inside. Also, asking what community I'm in doesn't make too much sense because I'm in multiple overlapping communities. And so there's fundamental work to be done here. And I'll talk just about a little bit about work on finding communities. So I'm going to take an example where this graph represents the adjacencies among vertices. And I made a very idealized situation where in the upper left-hand corner, everybody is connected to one another. And then there's another community where everybody is connected to one another and another. And there's no connections between communities. If you have a situation like this, you would find something which are called the singular vectors. And that's these vectors way over on the right. And the way you would identify the communities is you would map the rows of those vectors into a three-dimensional space. Now, this is kind of an idealized example, so everybody in one community gets mapped to one point. But if it was not such an idealized situation, if everybody in the community wasn't connected to everybody else, and there were some links between communities, what would happen is you would get mapped to points which are clustered about these centers. And then what you would do is use a method called k-means to actually find the communities. Now, one of the problems with this is if communities overlap, and now here I have two communities which overlap, what happens is you get 3 clusters instead of 2. And in fact, if you had n overlapping communities, you'd have 2 to the n clusters. So this isn't going to work too well. So instead of using clustering the rows, what you want to do is you want to find the singular vectors in the space spanned by those 3 columns of vectors. And once again, what you want to do is you want to find sparse vectors in the space spanned by those 3 vectors. And what that will do is that will pull out the communities. So this is another example where sparse vectors comes up. And what you want to find is you want to find the minimum zero norm vector. And, well, of course, that would be all zeros, so you require that there be at least one 1 in there. So let's say you want to find a community with me in, so you take my coordinate and say I want at least a 1 in that coordinate. Finding the minimum zero norm vector is there's no efficient algorithm for it, so we use a proxy, namely the minimum 1 norm vector. And what I've described is how you would find the global structure of a network. This is how you would divide this network of 100 million nodes into pieces of maybe 30 million or something like that. But what we want to do is modify this algorithm so we can find communities of size 50. And to do this, I'm going to give you a physical example of what we did. Suppose you had 3 ponds which were connected with little narrow isthmuses, and you dropped a little bit of dye into one of the ponds. If you looked at it immediately after you dropped the dye, you would know exactly where the dye was dropped. A little bit later, you wouldn't know exactly where it was dropped, but you would at least know which pond it was dropped in. And gradually that dye spreads out, and eventually it gets distributed over everybody. Well, what I'm going to do is, there's an analogy between this. Finding the singular vectors is looking at what happens when you do a random walk and you walk until it converges. But rather than wait until it converges, what I'm going to do is I'm only going to take a very small number of steps. I'm only going to take about 5 steps. Enough steps which is long enough to converge in a community of size 50, but not long enough to spread out into the entire network. And so if I do this, Then what I'm going to do is I'm going to find the minimum one norm vector in a subspace where I took maybe only 5 steps. I propagated that subspace. And what this does is this is a good way of finding communities. There are some research still needs to be done. The minimum one norm vector turns out not to be an indicator vector. It's not going to be a vector of ones and zeros. So you're going to have to threshold it. You're going to get a vector something like this, and you're going to have to decide where you're going to cut that threshold to find the community. And actually, you don't necessarily want to find a vector which is in that subspace, but what you'd least like to do is find a vector which is very close to that subspace. So what we did is we minimized the one norm of y, which is the vector we're trying to find, plus some constant times the cosine of the angle with that subspace. If you make that constant infinite, then you're finding a vector in the subspace.